The state of a system does not have to be represented by a single wave function. It can be represented by a superposition of two or more wave functions. An example from the macroscopic world is a vibrating string. Its state can be represented by a single wave or by the superposition of many waves. I will explain it more clearly, and this can be more visualized by this pictorial diagram. In quantum mechanics, an atom can be excited and not excited at the same time. Also, it can also be at the two positions at a time. You can see in the diagram. This ability to a superposition of state applies to any quantum particle, for example, molecule, photon, or spin, that small magnet carried by the electron. Let's focus on the atom. Its excitation can be visualized with energy levels. You can see in the diagram it can be not excited or can be excited at the same time or can be both at the same time also. So, but when one measures it, it will be only in any of the two states randomly. And to demonstrate that there is superposition, one sends an electromagnetic wave on the quantum object. When this wave is set with proper frequency, the atom alternates progressively between a non-excited and an excited state. And when we see all these together, the state of the atom is measured many times and averaged. Some Rabi oscillations appear, as you can see in the diagram. In real life, the quantum object is never completely isolated. For example, an atom can collide with other atoms or being coupled to electromagnetic fields. So the superposition of states stops after a while and the oscillations disappear. At the start, the atom can really be in two states at a time, but in the end, the atom can be only in one state at a time, randomly chosen. The time it takes for the superposition to disappear is called the decoherence time. It gives valuable information about the interaction between the quantum object and its environment and is crucial for quantum computing. Friends, quantum superposition is a fundamental principle of quantum mechanics. It states that, much like waves in classical physics, any two or more quantum states can be added together, and the result will be another valid quantum state. And conversely, that every quantum state can also be represented as a sum of two or more other distinct states. Mathematically, it is a property of solution to the Schrödinger equation. Since the Schrödinger equation is a linear, and any linear combination of solutions will also be a solution. Now, let us consider if psi1 RT and psi2 RT are two eigenstates which satisfy separately the Schrödinger equation, then the wave function given by psi RT is equal to alpha 1 psi 1 RT plus alpha 2 psi 2 RT also satisfy the Schrödinger equation where alpha 1 and alpha 2 are complex numbers. So, in general, according to the superposition principle, the linear superposition of any wave function give a new wave function which represents a possible physical state of the system and can be written as k psi is equal to alpha 1 psi 1 plus alpha 2 psi 2 plus alpha 3 psi 3 plus and so on. That can be written in terms of summation series as alpha I ket psi I, where alpha I are complex number and the quantity P is equal to modulus square of summation I alpha I ket psi I square represents the probability density for this superposition. Now, if the states psi I are mutually orthogonal, that means if psi 1, psi 2, psi 3 are the state and they are mutually orthogonal, that means brass psi 2 ket psi 1 is equal to 0 and brass psi 3 ket psi 2 equal to 0 and so on. Then the probability density will be equal to the sum of the probability densities of the individual state vectors. And this can be written as total probability density is equal to summation I alpha I ket psi square is equal to summation I alpha I square and that is equal to summation of alpha 1 square plus alpha 2 square plus alpha 3 square and so on. That is nothing but the probability of the individual eigenstate, probability densities of the individual eigenstates of finding the system in the state psi 1, psi 2, psi 3 and so on. From this it is clear that if you want to find the probability density of the system in any state psi 1, psi 2 or psi 3, then just you have to square the modulus of the coefficient of the corresponding state and we can get it clear by the example. Let's solve a problem based on this. Now the problem is consider a system whose state is given by ket psi is equal to square root 3 by 3 ket phi 1 plus 2 by 3 ket phi 2 plus square root 2 by 3 ket phi 3, where phi 1, phi 2 and phi 3 are the orthonormal sets. Now verify that this wave function ket psi is normalized and calculate the probability of finding the system in any one of the states phi 1, phi 2 and phi 3, and also verify that the total probability of the system is equal to 1. Now consider an ensemble of 8 10 identical systems, each one of them in the state psi. If measurements are done on all of them, then how many systems will be found in each of the states phi 1, phi 2 and phi 3? So let us solve this problem. So we have to find the system is normalized or not. So system is given in terms of the orthonormal sets of three vectors, that is phi 1, phi 2, phi 3, as the superposition of these states. So we have to verify that whether it is normalized or not. Since phi 1, phi 2, phi 3 are orthonormal vectors, that means phi j, phi k inner product is given by this data jk, where j and k is equal to 1, 2, 3 and so on. That means 1 phi 2 is equal to 0, phi 1 into phi 1 is equal to 1, phi 2 into phi 3 is equal to 0 and to 1, and phi 3 phi 1 is also 0, and inner product of phi 3 with itself is equal to 1. That is the condition for the orthonormal vectors. So let us find Poisson condition for system phi is equal to square root 3 by 3 ket phi 1 plus 2 by 3 ket phi 2 plus square root 2 by 3 ket phi 3 into square root 3 by 3 phi 1. So this will be star, which gives 3 by 9, 4 by 9 phi 2, bra phi 2 into ket phi 2 plus 2 by 9 phi 3 into phi 3, which is bra psi ket psi is equal to 1 by 3 plus 4 by 9 plus 2 by 9 is equal to 1 by 3 plus 6 by 9 is equal to 1. Ket psi is normalized. Now we have to calculate the probability of finding the system in any of the states phi 1, phi 2 and phi 3. So let's calculate the probability density P1 in get state phi1 that is given by p1 is equal to modulus square phi1 get psi square is equal to modulus of square root 3 divided by 3 bra phi1 get phi1 plus 2 by 3 bra phi1 get phi2 plus square root 2 by 3 bra phi1 get phi2 bra phi1 get phi3 square that gives 1 by square root 3 plus 2 by 3 into 0 plus square root 2 by 3 into 0 modulus square is equal to 1 by 3. Similarly, we can find the probability density of the system in get phi2 by p2 is equal to modulus square bra phi2 get psi whole square that can be given by modulus square root 3 by 3 bra phi2 get phi1 plus 2 by 3 bra phi2 get phi2 plus square root 2 by 3 bra phi2 get phi3 modulus square which gives p2 is equal to 4 by 9. Similarly, we can find p3 is equal to modulus of coefficient of phi3 square that gives 2 by 9. Since states phi1, phi2 and phi3 are orthonormal sets of states, therefore the total probability P can be given by the summation of the individual probability density P2 plus P3 that equals to 1 by 3 plus 4 by 9 plus 2 by 9 that equals 1 by 3 plus 6 by 9 that is equal to 1. Now consider an ensemble of 8-10 identical systems, each one of them in the state psi. And if measurements are done on all of them, we have to find the number of systems in each of the states phi1, phi2 and phi3. So let's find the number of systems in each of these states. So number of the systems that will be found in the state phi1 is given by n1 is equal to total number of identical systems into probability density of the system in state phi 1, that is P1. So 810 into P1, that is equal to 1 by 3, and therefore 810 divided by 3 is equal to 270. Similarly, the number of system that will be found in kit phi 2 is given by N2 is equal to total number of identical systems into probability density of the system in state phi 2, that is P2, is equal to 810 into P2 is equal to 4 by 9, that is equal to 360. And finally, the number of systems in the state phi 3 is given by N3 is equal to total number of identical system into P3 is equal to 810 into 4 by 9, sorry, 2 by 9, 2 by 9 is equal to 180. So friends, that how we can find the probability density for the superposition of a number of states, and also learned that the measurements, if the measurements are done on the system will be found in any of the states of orthonormal sets of vectors randomly. That means some measurements may be found in the sets of vector phi 1, some may be found in the set of vectors in phi 2, and similarly some may be found in the vector phi 3. So friends, these are the things for now which I wanted to discuss with you. These are the very important concepts on the superposition principle in quantum mechanics, and these concepts are asked in various competitive examination as well as in academics. So please learn this very carefully and practice the problem based on these concepts. And by learning through this video lecture, I hope you may be able to solve the problems based on this concept of superposition principle. Friends, if you have not subscribed this High Academy channel till now, please subscribe it and share this with your friends and colleagues. Thank you, friends.